How's everyone doing? Good. I just started the recording. We still have another minute or so. I might just wait around, see if anyone shows up. And look at that. Has anyone had any trouble getting appling? Has that been working okay? Lots of nods, that's good. How did first week of labs go? Pretty good? Yeah. Was the first one sort of just like an intro? Yeah. Makes sense. Did you use the software yet? The Beyond Labs? No. Yeah, some people have. I'm excited to see how that works out, just because obviously we've never used that before, and that's the plan for the semester, so we'll hope it works out okay. Where we were last class, you may remember on Friday, is we had no power, no electricity, so we ended up doing it on the board, and we kind of went through a little bit more in chapter 1 or unit 1, where we talked about Lewis structures, we talked about resonance structures a little bit, and I'm going to spend the first part of today's class talking more about resonance structures. Anyone who started the assignment already will have seen there's some questions on there about resonance structures, and the reason I'm maybe focusing a lot of attention on this is it's, I guess, a skill we find that a lot of students at a first year aren't super comfortable with, and it's something that's pretty important for this course. Particularly if you're doing Organic 2, it's even more important if anyone's planning to take Organic 2. So we're going to continue there. Just starting off with the first slide, just a couple of rules about drawing resonance structures. First of all, they only really exist on paper, as we talked about last class, meaning when you have resonance structures, none of the structures that you end up drawing are on their own a good representation of the actual molecule. The actual molecule is like a blend of all the possible resonance structures. And by looking at the resonance structures, we can, understand what the actual molecule is if you think of it as being sort of a blend of all of those structures that you've drawn. Okay, so the example I think we did in class where we talked about this molecule where you have acetate anion, and this would have a resonance structure. Notice the arrow I used here, it's the arrow that has the double-ended. Would have a resonance structure that looks like this. And I didn't rotate it, I didn't flip it, I didn't do anything like that. I left all the atoms exactly where they were, and I moved the electrons like this, where the pair of electrons from the oxygen on the bottom moved to make a double bond, and a pair of electrons that was part of the double bond in the upper oxygen moved onto the oxygen atom. Okay, so what we end up with is this. The real structure is like a 50-50 mix of the two. The real structure would look something like this, and maybe I'll put like a dotted line just to kind of say like half of a double bond, like 1.5 bonds for each of these, and each of these would be like -0.5. But that structure that I drew, that second one there, is kind of not really a Lewis structure, right? Like you can't draw dotted lines with Lewis structures. You can't put half charges. Lewis structures assumes that all electrons are like little hard dots or are part of bonds. You can't. In real world, though, we know you can smear an electron over multiple atoms. So that's what we're trying to represent with these Lewis structures. When you're pushing electrons around to look for resonance structures and to make resonance structures, you can't break sigma bonds. Sigma bonds are single bonds, right? You can break pi bonds, but not sigma bonds. All of the resonance structures on their own must be proper Lewis structures, unlike this guy. That's not a proper Lewis structure. That's sort of my attempt at drawing something that looks like the actual molecule here. All right, so the energy of the actual molecule is lower than the individual energy of each resonance structure. So, you know, the true real structure is, yeah, favorable because you can spread the charge out. And that comes from this idea that charge is bad, especially if it's built up in a single spot. So we want charge to be spread over as many atoms as possible. Notice I've been using what we call curved arrows or sometimes curly arrows. This is another type of arrow we like to use in chemistry. We'll be using a lot this semester. We have a lot of different kinds of arrows, right? Like I'm just going to for a second have an aside here. What does that arrow mean? Reaction. Yeah, you have A, it goes to B. We also have this one. No, not equilibrium. This one means resonance. We have an equilibrium one that looks sort of like that, which looks like this. Right? That's the resonance. Sorry, that's the equilibrium arrow right here. Now a new one we're learning is curly arrow. And what we use these arrows for is to show where electrons start and where they move to. Either when you're going between resonance structures, like you'll see today, or when there's a reaction and electron pairs are moving in that reaction as well. So we'll see all kinds of examples like this. There's other arrows too. We have arrows, I think we'll do them this semester, where it's like a curved arrow, but it only has half of an arrowhead at the end. And that's like a curly arrow, except it's for single electrons. We have one that looks like this too, which means whatever's on the left side is made from whatever's on the right side of that arrow. It's called a retrosynthesis arrow, which we probably won't use. But hey, if you're going on to do more, then you may see it sometime down the road. So basically what we're showing is, in this structure, you can see that there's these curved arrows that we're using. And what they mean is they always must start. Okay, the beginning of the arrow, or the non-pointy end of the arrow, must always be starting at an electron pair, which is either a lone pair or a bond. Okay, so it's got to start at a lone pair or a pi bond, not a single bond. It points to where those electrons end up, where they move to. Okay, these arrows don't tell you anything about what atoms are doing. They're not used to describe the motion of atoms, only the motion of electrons. So what you can see in the example that I have under here on the bottom of the slide is there's a curly arrow that's starting on the bottom oxygen, and you can see it's starting at a lone pair. And it's pointing from the lone pair to the space between the carbon and the oxygen. So what that means is that electron pair is leaving the oxygen atom. It's no longer a lone pair on the oxygen, and it's going between the two atoms, meaning it's going to form an additional bond between those two atoms. So in the structure, in the product, notice over here, we're down to two lone pairs, and there's a double bond. That's what that means when we push this curved arrow right there. It means we're taking the electron pair, it's gone in the product, and then we're making that second bond out of it. And then you notice on the upright oxygen that's pointing up here, we have another curved arrow that's starting between the carbon and the oxygen. So that means we're taking an electron pair that's in that bond, and we're pushing it up onto the oxygen. So in our product, the oxygen should have 3 lone pairs now instead of 2, and that double bond should go down to a single bond. Okay, so that's what we're doing with these curved arrows. And then the curved arrows on the right structure are showing you what you would need to get back to your starting material. So showing how the electrons sort of move back and forth between these two different structures. We're going to use curved arrows a lot, and we're going to harp on you probably a lot about correctly using these because they're very often used incorrectly. Okay. So here's an example of resonance. This is the carbonate anion. Carbonate is what you get if you dissolve carbon dioxide in water, which of course happens in the oceans a lot. Carbonate, you can see that clearly. It's got negative charges on these two bottom oxygens, and then there's a double bond to the other oxygen. Everything has a full octet. These are great resonance structures. These are the three structures I'd expect you to draw. If I gave you the carbonate ion and I said, draw all the resonance structures of this, they should all be connected by these double-headed arrows. But what we need to do, what we're being asked to do, is use the curved arrows to show how you get from one structure to the next. So in the first one, going from 1 to 2, what you can see is the top oxygen has gone from 2 lone pairs to 3 lone pairs, right? So that means a pair of electrons must have come up onto that oxygen, and where they must have come from is the double bond, because the double bond went from double to single. So we're going to take our pair of electrons, we're going to start it here, and we're going to push it up onto the oxygen. And it doesn't really matter. I kind of curved all the way around and then came down from the top. I could have kind of snuck in on the side and pointed to the oxygen. It doesn't really matter. I could have taken a long path and then eventually gotten back. All that matters is that you start where the electron pair came from, and it points to where the electron pair goes. There we go. That single arrow I've drawn means that in the product, that double bond will become a single bond, and the oxygen up top will go from 2 pairs to 3 pairs. Very rarely do these curved arrows come on their own, especially for resonance structures. Usually you need 2 or more. So there's other changes that are here as well. The right-hand oxygen, this one here, notice that it has 3 lone pairs in compound 1, but only 2 lone pairs in compound 2. And notice that carbon-oxygen bond went from single to double. So there's another pair of electrons that moved going from compound 1 to compound 2. So what we're going to do is start with a lone pair on compound 1. Doesn't matter which one you pick. And we're going to point that one down to the space, just somewhere halfway between the carbon and the oxygen. Okay? And it's important that you pick that spot well. Like some people would have a tendency to point it like there, where it's like kind of not super clear what you're pointing to. Is that between the 2 atoms, or is that pointing to the carbon? It's not really super clear. I'm going to erase that before I get too far. Get out of there. Okay, so now we're done. That's it. That's showing everything going from compound 1 to compound 2. The left-hand oxygen doesn't change from 1 to 2, so we don't have to do anything to that. Now, going from 2 to 3, we have to look and see what changes there are there as well. Notice that the left-hand oxygen goes from single bond, 3 lone pairs on the oxygen, to double bond, 2 lone pairs on the oxygen. So what that means is an electron pair, one of the lone pairs has gone to become a bond. That would look like this. Okay. Starts on the electron pair, goes to where the bond forms. And then you look to see where they went. Well, you can see the double bond going to the right in structure 2. The oxygen has gone from 2 pairs to 3, so electrons ended up on that oxygen on the end. And you can see the double bond went to a single bond. So that will look like this. So that would complete that structure. That would show you how the electrons move from compound 2 to compound 3. The reason we use these, by the way, like why are you making me memorize all these curved arrows and how to point them and so on? It's because when we start doing reactions, it gets kind of complicated trying to understand what's happening in a chemical step. But if you're shown exactly which electrons are moving where, it becomes very straightforward. You can look at it and say, oh my God, that's all that's happening. These electrons are coming down here, and that's the reaction. Right? Where otherwise, it can look kind of complicated. I'm going to show you an example of a reaction. This is one that we'll do in organic 2. It's called a Diels-Alder reaction. Won a Nobel Prize. If you start with a molecule like this, skill testing question, how many hydrogens are on this molecule? I hear 4 and I hear 10. Both wrong. There's 6. There's 6. There's a hydrogen here and a hydrogen there. One here, one here, one here, and one here. Because each carbon needs enough hydrogens to make a full octet. And this can react with a molecule like that. That's called, how many hydrogens are on this compound? 4, right. So that's 6 and 4 hydrogens. Hydrogens don't matter here. What's happening is these will react, form this. And a lot happened here. A lot of bonds broke, a lot of bonds formed. We went from 2 molecules to 1. We kept all our carbons and our hydrogens, but it's not maybe super obvious what happened in a reaction like this. But if I show you the electron pairs, it might make a lot more sense. So what's happening is there's sort of this cyclic where the electrons are kind of in one place and they just kind of go, whoosh, they all switch over one spot. That pair of electrons here goes to the space between that carbon and that carbon to form a carbon-carbon bond. These electron pairs in the double bond move over, I guess, I didn't draw that super well, but these electrons move here between the carbon here and the carbon here to make a bond, and the electron pair moves between this carbon and this carbon to make another double bond, and you get your compound. So we're going to see examples that maybe are a little more complex than the ones we're looking at here, but we'll see lots and lots and lots of examples of curved arrows being used. Back to the idea of resonance structures. The ones I've showed you so far today are all identical, right? I'll show you 3 structures that look the same, that look like maybe rotations of the same molecule, but that's not always the case. In fact, often it's not the case. And we usually like to simplify it to show you structures like that in first year, but we're going to be showing you more advanced examples, I guess, in this course. And that's just the nature of organic chemistry, because organic chemistry, often the molecules are, I guess maybe from your guys' experience, large. You know, they might have 10, 12, 20 atoms. But, and so when that's the case, there's more atoms you have to kind of think about or worry about or keep in your head. When you have different structures that are not identical, there's a few rules that we use. One is electronegative atoms. It's better to have them on an electronegative. It's better to have a negative charge on an electronegative atom than to have it on a more electropositive atom. I'll show you an example of that. If there's a positive charge, it's better to put it on an electropositive atom than an electronegative atom. And how do you tell how electronegative an atom is? Yeah, you look at the periodic table. If it's up and to the right on the periodic table, it's increasing in electronegativity. What's the most electronegative atom? Fluorine, that's right. Arguably helium would beat it, but helium doesn't form bonds, so we don't really worry about its electronegativity.
Is this the opposite rule? Do you have like the odd electron is like a lone pair and just one single?
So yeah, the question was, what are the rules if you have a single electron, like a free radical? A free radical, if there's, that will also be an electron pour, so it's the same, treat it like a positive charge. Generally speaking, it's better to have atoms obey the octet rule. There's some exceptions to that. I think like we saw with boron. Boron often does not have a full octet, as we'll see. So here's an example. These are two compounds. Well, it's not two compounds. This is one compound with two resonance structures. And the first thing we want to do here is we want to use curly arrows to show how you get from the left structure to the right. So we're going to kind of break this down. You're going to look at the left-hand nitrogen. It has two lone pairs and two single bonds. And in the product, or in the right-hand structure, it has one lone pair, a double, and a single. So we know right away it's lost a lone pair, and it's gained a pi bond. It's gained that second bond between the nitrogen and the carbon. So we know there's got to be an arrow that looks like that. Starts at the lone pair, goes halfway between the nitrogen and the carbon to make that double bond. Next, if you look at the next carbon over, there's a CC double bond that's gone in the product. I shouldn't say product. It's not a product. It's the same molecule. It's just a different representation of the same molecule. But notice the next CC bond went from single to double. So basically what's happened is we've taken the pair of electrons that started on the double bond there and moved it over between the carbon and the carbon. Now we have the CO. It's a double bond CO with two electron pairs on the oxygen. And in the product, it's not a product. In the second structure, we have the oxygen with three lone pairs and then a carbon-oxygen single bond. So what's happened is an electron pair started in the pi bond and moved up onto the oxygen. So those arrows show you how you get from the left-hand structure to the right-hand structure. These are resonance structures, which is why we use this arrow. The real structure is, a blend of the two. Is it a 50-50 blend? No. It's 50-50 if the two structures are identical, like they were with acetate. Then it's exactly 50-50. But here they're not. And we might have the question, as you see on the bottom there, which of these two is better? Which is better than the other? Everyone said the second one. Great. And that's because the best structure is the one where the charge is on the more electronegative atom, right? And because the periodic table goes boron, carbon, nitrogen, oxygen, fluorine, electronegativity increases in this direction. Oxygen is more electronegative than nitrogen. That means this structure is the preferred, or what we would say it's the larger contributor. So the real structure might be a 25-75 blend of these two, where the actual structure might have 0.75 of a charge on the oxygen and 0.25 of a charge on the nitrogen. So the left one contributes, it stabilizes the molecule, makes it a more stable molecule than it would be without that. But if you had a single structure you could choose to best represent the molecule, the right-hand one would be better than the left. We're doing great. So when you start drawing these structures, usually like students don't quite know where to start. And if you pick a good starting point, the in-between steps can then kind of flow more naturally, especially as you do some practice and do more examples. You'll start to see where electrons should be going. It'll become more intuitive. But generally speaking, a good place to start is look for, if there's a negative charge, start there. Okay, that's your first arrow should almost always be at a negative charge if there's a negative charge on the molecule. Or in other words, if there's a positive charge, that's where your last arrow should end up. Right? So you can start, you can go backwards if you want. Now the example that I have here doesn't have a positive or a negative charge. But what it does have is some pi bonds. So pi bonds are good. Pi bonds we can turn into lone pairs if we want. And we also have some lone pairs that we could potentially move as well. So just based on the examples we've seen a number of steps where we have a carbon double bond oxygen and 2 lone pairs where we've moved the pi bond in the double bond over to the oxygen. So that's a place we can start here. Or you could look at the left side of the molecule and say, well, there's a lone pair on the nitrogen. That's maybe a place we could start as well. We could start either place. So why don't we start on the carbon going to oxygen, like that. In our product, that's going to look like carbon, oxygen, lone pair, lone pair, lone pair. And there's going to be a negative formal charge now on that oxygen. Why? Just rules of formal charge. The CH3 we have not changed. That would put a positive on that carbon. And you have this structure. Is that a good structure? Well, good is a subjective term. It's good, I guess, in the sense that it obeys all the rules. I didn't mess up. I didn't put arrows in the wrong place. I didn't put any charges in the wrong place. So it's correct. But we can do better than that. That has a carbon with a positive charge that doesn't have a full octet. That's not ideal. Can we draw a resonance structure that has a full octet? Well, what we could do is we could take this bond and move it over between those 2 carbons, right? A pi bond, you can move just one space over like that. And then you can have a carbon-carbon double bond, and we can take our lone pair off the nitrogen down like this. So I didn't leave myself a lot of space, but that would give you H2N double bond now to carbon, hydrogen. This would be a single bond carbon, hydrogen, double bond carbon, oxygen, negative, CH3. Should there be any other charges anywhere? Right, +1 on the nitrogen. Charges always have to balance, right? So the total charge on all of these structures has to be the same. So this structure here is a resonance structure of the first one, as is this one. The top one's better though, a lot better, because all the atoms have a full octet in the top structure, although the bottom left structure, our original structure, is by far the best. Right? There's another one you can draw as well. You can move that double bond over, but not move the electrons off the nitrogen. That would give you a 4th resonance structure. Generally speaking, though, we don't bother drawing resonance structures if they're like crappy, if they like basically don't contribute at all, if they're like a 1% contributor or less. And those percentages, like, I'm just guessing what those might be. But if you have one that sort of has a real bad flaw, you know, like having a carbon that doesn't have a full octet, when all the other structures everything has a full octet, we probably wouldn't bother drawing something like that out. Although I do believe there's one question on the assignment, maybe the last question on the assignment on sapling, where it's asking additional resonance structure when it looks like there may not be any more, but it wants one that has a carbon without a full octet. Great. Sage advice, and this is something I'm going to recommend you guys do, especially when you're starting out, is we're kind of teaching you multiple things at the same time. And one of the things that, and I was back to this before, that we just went through is bond line structures. And I'm going to be using almost exclusively bond line structures in this course going forward, and you guys have very little experience with that. And so when you're drawing resonance structures, a great first step is to draw in all of the hydrogens that aren't shown, because that'll help you not make mistakes. So if you're given an example like this, draw a resonance structure for this, well, let's add all our hydrogens so we don't screw up, because we can't move atoms when we do resonance structures. So I'm going to just redraw this. Well, I'm not going to redraw it at all. I'm just going to draw in the hydrogens. There's 2 hydrogens there, right? It needs 4 bonds. Same with this one. When carbon has 4 single bonds, sometimes we say the carbon is saturated. Can't make any additional bonds to it. This is unsaturated. It has 3 bonds because you could potentially turn the double bond into 2 singles. That's where the phrase comes for like saturated fats and unsaturated fats. Saturated fats, all the carbons have single bonds. How many hydrogens on this carbon? It's just 1. There's 1 and there's a lone pair. How do you know that? Well, it's got a negative charge. You see the negative charge that's in there. You can't have a negative charge and have 4 single bonds on carbon. If you do the calculation for formal charge for carbon, it starts with 4, right? 4 is the number of valence electrons for carbon off the periodic table. Subtract the number of bonds. Subtract unshared electrons. And that has to equal -1. And we know the number of unshared electrons is going to be 2 in the lone pair. And then the number of bonds that it can form must be 3. So we have 1 bond to hydrogen, a lone pair, and that's the structure. Now we can draw the resonance structure, and what we're going to do is we're going to start at a lone pair. We're going to start at the negative charge, which is the best place to start if you have a negative charge. And of course, we have a negative charge. There's a lone pair of electrons there. In fact, I think it's impossible to have a negative charge without having a lone pair of electrons. Certainly on carbon, that's true. So what we can do is we can take those, and you can see there's a double bond that's just adjacent to it. What we can do is push those lone pair of electrons down and make the double bond. So what we can do is start here and do something like that. We're pushing those electrons starting at the lone pair of electrons, and that will give us a structure that looks like this. And we can draw in again all of our hydrogens that we had to begin with, because remember, we cannot move atoms when we do resonance structures. So now what we would have is a double bond between those two, and the pair of electrons we moved over onto this carbon. And you have this structure that you see right here. Cool. Why do we do that? Well, it looks the same. We just kind of moved it. It's because the real structure, the true structure, doesn't have a negative charge on that one carbon. It's split over 2 carbons. And you might be looking at this as like, this is a weird example because carbons make 4 bonds. Carbons don't have negative charges and lone pairs and all these sorts of things. Well, we're in organic chemistry now where carbon does all sorts of things. In fact, people spend a lot of time trying to make carbon, forcing carbon into these weird, I guess, structures like you see on this one, in order that it'll do some reaction that we want to make some product that we want. Okay, so we're not going to be just dealing with well-behaved carbon atoms that always follow the octet rule, that always have formal charges of 0 and all these sorts of things. We're going to look at a lot of weird variations of carbon atoms. In particular, there's 3 that we're going to be looking at in a lot of detail in this course. One, we call them carbocations. They are carbons, I'm going to get off red here, carbons with positive charges. These are the ones you're going to see the most. We're going to see carbons with negative charges. We're going to see carbons that are neutral, lone pair, and just 2 bonds, called carbenes. And it's because carbon can do all these weird and wonderful things that allows us to do a lot of interesting reactions and make new things, build new molecules. It's kind of like Lego. You know, we have all these pieces, we can build up these structures, and hypothetically, we can make anything. We can make any molecule as long as that molecule is stable. As long as it's makeable, potentially we can be making it. All right, some more practice. I mean, I think we've seen this top example a million times by now. This is acetate. Start from a negative charge and lone pair and move. And then we're going to start at the thing and move over there. So the most you can move a pair of electrons is like one space. You can't move it very far. If you have a long molecule, you know, if you have a molecule that's like O minus, you can't just go like this and put a pair of electrons way over on the other side. You can only move it at an adjacent spot. You can only move it like maybe here, here, here. You can get those electrons there, but you got to go through the molecule. You got to follow the path. Anyway, that has nothing to do with this question. I'm going to convert it to bond line in the same breath. The bottom molecule, does anyone recognize that molecule? Ozone, yeah, this is ozone. What's the hybridization on the central oxygen of ozone? sp2. So again, what we want to do here is move a pair of electrons on the oxygen to the adjacent bond. We can't just stop there, though. If we did stop there, that oxygen would have 5 pairs of electrons around it. That would exceed its octet, and you cannot exceed the octet for oxygen because it's in row 2. So what we need to do is then take the pair from the OO double bond and keep moving them. And we can move it onto the oxygen, and you end up with, no, I made a mistake. Let's go back. Okay, I can get my pen back now. Oxygen, oxygen, 3 lone pairs now. That lone pair hasn't moved, 2 lone pairs. And if we want to put our charges in, they look like this. So what's the charge on the central oxygen in the real structure? +1. It's +1 in the left structure, it's +1 in the right structure. The average is +1. What about the outer oxygens? What's the charge on each outer oxygen? -0.5. That's good. You guys are nailing it today. Now, one like this. This looks like something more like one of the sapling questions. Draw 3 additional resonance structures of the following molecule. First, convert to full form. Full form, I just means put all the hydrogens in. So I'm just going to decorate this structure with hydrogens. This is a useful exercise, just so you know how many hydrogens there should be. Did I miss any? I did. How many did I miss? Just 1. It goes here. Now, it pained me to draw it the way I just drew it because that carbon is sp2 hybridized. Positive charge carbon is sp2. That means all the bond angles there are 120 degrees. And I drew that as some weird-ass angle. It's not 120 the way I drew it. I didn't want to draw straight on top of the charge, so I kind of pushed it to the side a bit. But yeah, that's the actual shape. So we want to try to find some additional resonance structures. We have a positive charge. If you have a positive charge, first thing we want to think about is, are there nearby electrons we can push in? That's either an adjacent atom that has a lone pair or an adjacent atom that's making a multiple bond. So yeah, we have an adjacent atom that's making a multiple bond. In fact, we have 2 of them. Both atoms adjacent to the positive charge are making double bonds. So what we can do is we can move, say, this one over, And I'm pointing it halfway between those two carbons. I'm not pointing it to an atom. It's going between them because it's going to make a double bond. And what this will make is something like this. Hydrogen, hydrogen, hydrogen. If something doesn't have an arrow associated with it, it didn't move, it shouldn't change. But we now have a double bond here. And the positive charge goes over there. So what I've done is move the charge over one place. Oh yeah, another double bond here, isn't there? Can we do it again? Yes, we can. We can take the next double bond and move it over. I'm going to swing this one out here just to give myself a little bit more space. Single bonds can rotate, so we can swing that around if we want. So now we have a double bond here. And the charge has moved now over here. Can we keep moving this? Sure, why not? Can move that one over. Maybe I shouldn't have rotated that just because I finished telling you that atoms don't move in resonance structures, and I went and I moved some atoms. I just rotated them though. I didn't like break bonds, or I didn't, you know. I apologize, but I did break a rule I just told you, didn't I? Okay, so that means there's now a double bond here, and the charge goes over there. And all this question asks for is 3 additional structures, so we're done, but we can do it again. One more time. We can take this double bond and move it over there. There's a hydrogen here too. Plus there. I think that's it. We can make ridiculous ones. Like we can just, well, why don't we take this and put that there? And leave everything else the same. Well, then you can have this structure where you have like, okay, we have a positive up here, we have a lone pair here with a negative charge, and then we have some things, and then we have positive down here as well. Like, yeah, you can draw things like this, which are correct in the sense that they don't disobey any rules, but they're not an important contributor because we now have 2 positive charges. We have a positive charge and a negative charge next to each other that you can collapse to make a bond. We have 2 carbons that don't have full octets. Where the negative charge is, it's on a carbon, which is not particularly electronegative. It's got a lot going against it. So structure like that, just because you can draw it doesn't mean you should draw it. You have to just apply some, and this is where experience and intuition will guide you well as well. All right, how are people with that? We're done. Unit 1 is done. Important stuff that you guys need to get from this chapter, first of all, is drawing Lewis structures, right? We have a tutorial online, and lots of practice doing that. Looking at a structure that you've just drawn and identifying the hybridization. SP, SP2, SP3. And we're going to use that immediately in our next chapter. going from regular full-on Lewis structures with all the lone pairs and everything, back and forth between those and condensed structural formula and bond line structures. It's important that you can do that too. And resonance structures as well, of course. So these are all the things that we at least introduced or touched on in first year, but we're going to be using quite a bit in this course. So it's best to make sure you've mastered this early, and so that when we're going to be pulling these out of our toolbox later on and applying them to reactions, you're going to be good at it. You're going to be good at it already. All right. Swipe forward to exit. Okay, so I have all right. What are you doing to me, PowerPoint? Don't freeze. Come back. I don't want this one. I want back. Unit 2. So I'm going to introduce Unit 2. We only have like 10 minutes or not even 5 minutes left. But what we're going to be doing is looking at molecules that we're going to be using a lot in organic chemistry. And we're going to be looking at molecules, and these molecules do have multiple atoms, and we're going to be breaking up the molecule into pieces and looking at those individual pieces, and we're going to be looking at what we give names to, how we identify these parts, what we call them, and what, I guess, function those parts give to the molecule. So one thing that we find a lot in organic chemistry is, carbon and hydrogen are super common. Carbon-carbon bonds, carbon-hydrogen bonds, super common in organic compounds, but they're not very reactive. They're quite boring chemically, in fact. Carbon-carbon bonds, they're not polar. They're very stable, very high energy. So if you all have carbon, hydrogen, and single bonds, there's not a whole lot the compound will do. If there's other atoms, we call them heteroatoms. Things like nitrogen, things like oxygen, sulfur. Those typically are polar. They're much more reactive than carbon single bonds or carbon-hydrogen single bonds. And so we say that these are the parts of the molecule that gives the molecule function. So we call them functional groups. Carbon-carbon double bonds as well. We said these in a previous class, these are much more reactive than carbon-carbon single bonds. That's because pi bonds are weak compared to sigma bonds, because the overlap of those side-on p orbitals isn't very good. So if you have carbon-carbon double bonds or triple bonds in the molecule, those are also what we would call functional groups. Those give the molecule function. They give us sort of a handle where we can go in and do a reaction if we wanted to do it. So we're going to be looking at all of the different functional groups that we're going to be seeing. And we're going to also be looking at the intermolecular forces that these functional groups provide for these molecules. If you look at biomolecules, molecules that are common in biology like nucleic acids or proteins or things like this, they're full of heteroatoms. They're full of functional groups. And if you had just a big molecule that was just carbons and hydrogens with single bonds, it wouldn't really do anything, right? So you need these functional groups in there. It also wouldn't be soluble in water, so that's an important consideration, especially when you think for organic chemistry. Most organic compounds are made by living things for some functional purpose inside of an organism. And because water is the solvent where almost all biological reactions take place, molecules without functional groups are not that important in biochemistry, for example. Right? We want oxygens, we want nitrogens, we want hydrogen bonding, we want interactions with water, we want all these sorts of things on these molecules so that they can do this. So we're going to be looking at intermolecular forces. Intermolecular forces are just forces of attraction between different molecules. And I mean, I had it on the previous slide. It all comes down to this one equation, Coulomb's law, which just says that the force between two atoms, the force of attraction or repulsion, depends on the two charges and the distance between them, r squared. So basically what that means is if you have a positive charge on one molecule or a partial positive charge and a negative charge on another partial negative charge, they will attract each other. If you have two positive charges, they'll repel, or two negative charges, they'll repel as well. So all the intermolecular forces comes down to that one thing. Okay? Like charges repel, unlike charges attract. And we break it up into sort of subtypes, but this is all just sort of variations of that same thing, positives and negatives attracting each other. If you have ions in solution, ions will strongly attract other ions by a type of intermolecular force we call ion-ion. Very clear name, very obvious what it means. So you can have an organic anion. What's that one called? It's acetate. It's the conjugate base of acetic acid. And then we have a sodium, which is a positive cation. We have organic cations too, though. We can. Why don't we take something like, this one's called the tetramethylammonium cation. There's lots of cations that we could use. And if these happen to be dissolved in solution and they come close to each other, they will attract each other. Okay. Ion dipole forces are when you have a polar molecule, a dipole, say. Like in this case, that molecule is called acetone. Acetone has a carbon-oxygen double bond, and that's very polar because the oxygen is much more electronegative than the carbon. So you get this polar bond form, and the negative end of that bond will be attracted to positive cations that might be around, like sodium or whatever. So this is ion dipole, and this is weaker than ion-ion, and that's because ion-ion has like a full positive and a full negative that are attracting each other, whereas ion dipole has a full positive and just a partial negative. Or it could be a full negative and a partial positive. So because the charges are not a full charge, they're a little bit smaller, these ion dipole forces will be a little weaker. I'm just noticing the time here, it's 9:21, so I think we're technically done. We're going to start Wednesday's class. We're going to go through all, as a review, the intermolecular forces, and then dig in to start introducing us to the functional groups in organic chem. Thank you very much. I have office hours that'll start around 9:30 this morning. I realized I left my key card to get into my office at home, so I'm going to just drive home, which is 6 minutes, and then I'm going to open up Teams. So if I'm not right on at 9:30, I will be by 9:40 for sure. So if you want to get in touch with me there and ask questions, that'd be fantastic.
Are you going to send me a class link?
Yes, so I'm going to make that up today to the class schedule. If you haven't gone onto our Acorn site yet and filled out that question, I think most people have, but if you haven't answered that, please go ahead and do it, and I'll put out the schedule for the next couple of classes coming up. Thank you very much.